We'll now look at the short answer questions for acids and bases, Module 6. We'll start with this question here. It's a fairly simple question. It asks you to write equations to show that potassium dihydrogen phosphate is an amphiprotic substance. Now, while the question itself is quite straightforward, we might just want to make sure we understand what this is saying. Amphiprotic means that it can either donate or accept an H+, right? Protic for proton. Amphi, so either or, like, both, right? So you want to write equations to show potassium dihydrogen phosphate. Now, the thing with potassium dihydrogen phosphate, did you have a question?
No.
So the thing with potassium dihydrogen phosphate is that the potassium is really not really doing anything. It's just a spectator. So it makes much more sense to just focus on the dihydrogen phosphate part. Dihydrogen phosphate means it's H2PO4-. If you want to show that it can donate, and let's just make it sort of more obvious, I suppose, with an OH-. If you want to show that it can donate to a base, we'll just draw this out. It's going to become HPO42- plus H2O. Okay, so that's the donation. Alternatively, it could accept one. And again, it's in equilibrium because it's weak. So this here is it accepting one. Right? You've got it donating one, you've got it accepting one, right? And that's it. So here, it says the Arrhenius theory of acids and bases could not explain why ammonia is basic when dissolved in water. The Bronston-Lowry theory does explain the basic nature of an ammonium solution. We want to describe the differences by which Arrhenius and Bronston-Lowry define a base. So we'll talk about what Arrhenius did, right? If you want to describe the differences, you at least need to know what Arrhenius did and what Bronston-Lowry did, and we'll then focus on the difference, right? So Arrhenius defined a base based on the species that would be formed when the substance is dissolved in water, specifically the formation or the dissociation to form hydroxide ions. Bronston-Lowry, on the other hand, Bronston-Lowry definition does not depend on the species formed in solution, but just based on the fact it can accept an H+. If it's a proton or proton, right? If it can accept a proton, then it is a bromellary base. That's it. For 1 mark, why wasn't Arrhenius able to explain the basic nature of NH3 in water? Well, basically because it doesn't form OH minus ions in solution, right? Ammonia dissolved in water. Ammonia, right, does not have hydroxide. Right? Ammonia does not contain hydroxide. Therefore, it is not possible to dissociate and release and liberate hydroxide ions. So it cannot be explained using Arrhenius' definition. I mean, we just talked about it earlier, right? Arrhenius' definition in part A was that you would form OH minus ions in solution. Well, you don't have, right? You don't have OH minus ions in solution. You don't have OH minus ions to give out in ammonia. And that's why you won't be able to do that. What's that sound, by the way, Jose?
Pardon?
What was that sound earlier?
What's that?
No, there was like a sort of sharpish screech or something.
Not too sure.
Okay. 2, Carbonate theory is able to explain this phenomenon. Write an equation to illustrate this. Okay. It's only asking for an equation. So you just really need to show the NH3 accepting so all they really want here is for you to do this. So this here is your ammonia on the left. You put it in water. It accepts the H plus from water, right? You don't need to write in this red one in your exam. This is just for an explanation purposes. You donate, the water donates an H plus to the NH3. So this then becomes NH4 plus, right? Well, this water becomes OH minus. Once it's given off an H plus, it's given away a proton, you're becoming hydroxide. The ammonia accepts the proton and becomes ammonium. Okay. So this question has told us that we've dissolved 1.25 grams of calcium hydroxide in 1.5 liters of solution of water. You want to calculate the pH of the solution. Now, given it's calcium hydroxide, which has marginal solubility, I'm a little doubtful if we can actually dissolve 1.25 grams in 1.5 liters of water. But look, the question has told us that we can, and we possibly could. We could do the calculation to confirm it, but we won't need to here. For our purposes here, we'll just assume that you do, because the question tells you do. So if we dissolve 1.25 grams of calcium hydroxide in 1.5 liters of water, let's find the pH. Well, to find the pH of this, you just need to understand that calcium hydroxide has this formula. Why do you even have a pH? Well, because it will then dissociate as a strong base to this, to calcium ion and hydroxide ions, 2 of them in fact. And because it forms hydroxide ions, then it's going to have a pH, because pH basically measures H plus or OH minus ion concentration. Now keep that in mind, it's related to concentration, right? So we know the mass of the calcium hydroxide that we're dissolving is 1.25 grams. We need to go from that to the number of moles. Now the number of moles will be the mass divided by the molar mass, which is 1.25, divided by, well, the molar mass of calcium hydroxide, you need to add it up. So I think it's around 40 plus, 16 plus 1 times 2, pretty much. So it should end up being around 74, but we'll quickly check that against the periodic table. So you can pull that out.
$74.093.
Did you just look it up or did you calculate it?
Oh, I just looked it up.
Yeah.
And how you calculate it.
Yeah. So you need to make sure you actually know how to do these. Without, when you do an exam, you won't have the luxury of looking it up, all right?
Yeah.
Sorry, my computer's just taking a little while to load up the thing. Okay. So it's 40.08 plus 1.008 plus 16 times 2. Okay. And so we, of course, would then calculate that. And giving us an answer of 1.69 times 10 to the -2 moles. We've now worked out the number of moles of calcium hydroxide. Now, the number of moles of calcium hydroxide is that, but the number of moles of hydroxide will be 2 times the number of moles of calcium hydroxide. Just look at the equation we wrote above here, right? You've got calcium hydroxide, which should have a 2 there. That appears to be missing. Will become CaH2 plus 2OH minus. So the number of moles of OH will be double this one. And so that would then be 3.37 times 10 to the -2 mole. Now you've got the number of moles of this, but to get the concentration of OH minus, it's going to be N over V. That's how you work out concentration. So that's going to be 3.37 times 10 to the -2 divided by 1.5 liters. And that gives you an answer of 2.25 times 10 to the -2 mole per liter. Now, they did give you 3 marks. And if you take a look here, this is 3 significant figures. This is 2 significant figures. So it may be better to round it to 2 significant figures. And more appropriate because you always basically quote to the, oh, okay, actually, we don't need to because it's, we actually haven't finished the question. And don't round before you finish the question, right? Don't round before you finish the question. So this is OH minus, okay? So we will then work out POH, which is negative log base 10 of OH minus concentration. And that gives you an answer of 1.65. Now pH is just 14 minus pOH. And that's going to be an answer of, well, 12.35. And that would be your answer here. Great. Moving on. So in order to maintain a suitable pH in swimming pools, a buffer such as sodium hydrocarbonate or carbonic acid is added to the water. This keeps the pH range between 7.2 and 7.8. Write an equation to demonstrate the buffering action of sodium hydrocarbonate to control the swimming pool pH. It says write an equation. So it talks about the hydrogen carbonate and carbonic acid. Since it's talking about just one equation, you're going to have to involve both of those two. And really, it's the carbonic acid H2CO3 in equilibrium with water. Okay. It will be in equilibrium with a hydrogen carbonate. And that will give you an H3O plus. So whatever equation you write, you want to have the hydrogen carbonate and the carbonic acid both there. Okay. That will demonstrate the buffering action because this is an equilibrium situation. It's incomplete, which means if you have a high amount of hydrogen ions, then it will shift left and therefore reduce it. If you have a very basic situation, then you've got a low amount of this and you'll shift right and correct it that way. And that's why the buffers work. The buffers make use of your equilibrium situation to push and balance it out, to make it so that it can, within reason, within the buffering capacity of the buffer, keep it with the pH within a relatively narrow range, despite the addition of small amounts of acid or base. This question now asks you to calculate the pH of 1 mole per liter of hydrofluoric acid solution, given that the pKa of HF is 3.18. Okay. So for 3 marks, we'll need to start with pKa. And we'll also recognize that hydrofluoric is a weak acid. I'll just use Arrhenius' definition, which is sufficient for our purposes here. So pKa is 3.18, which means Ka is 10 to the negative 3.18. So that means it's going to be about 6.61 times 10 to the negative 4. Now, what does Ka represent? Well, Ka represents the K to this particular equation. So that means it's H plus times F minus, your products, over the reactants here. So that's what it represents. Now, you've got a 1 mole per liter solution of HF. And this is where your ice table will come in handy. And you'll need to deal with it for H plus and F minus and HF. In fact, I'll write it in this order. Now, the idea is simple. You're told you've got 1 mole per liter of HF. So at the start, you can basically think of it, you've got 1 of those, and essentially you've got none of these at the very, very start. Now, of course, HF will ionize some of it. And if some of HF ionizes, what that then means is you're going to lose some, right? Some of it will go across. We don't know how much, but if it goes across, then this will go down. And because it's 1 to 1 to 1, this will go down while these will go up by the same amount, leaving you with 1 minus x at the end, or equilibrium, and x, meaning this expression can be expressed as x squared all over 1 minus x. And this Ka is this number. Now, from chemistry point of view, we don't need to solve this quadratic, not in this current form. We just say, because it's weak, we expect x to be much, much smaller than 1, and therefore 1 minus x is approximately 1. Therefore, x squared is approximately 6.61 times 10 to the negative 4. So x is, for our intents and purposes, going to be 2.57 times 10 to the negative 2. And importantly for us, that's for the concentration of H+. From there, we can get pH quite easily. Just take the negative log base 10 of that. And the answer to that will therefore be 1.59. Because it's weak, it doesn't ionize much, right? And because it doesn't ionize much, X is quite small. Like it's a lot smaller than 1, like 0.0001, for example, right? It's a very small number. Okay.
Yeah.
I mean, you can see when we calculate it, it's a relatively small number. It's much, much, much smaller than 1. Because much smaller than 1, to make the question easier, we then say, 1 minus x is approximately 1, because x is such a small number, right? That's a simplification you do when you do these questions in chemistry. You can work it out exactly, so-called, like using quadratic formula and so forth, but you're not expected to do that in chemistry. And you should find that it should make no difference to your final answer when you work out the pH. Not in the first few decimal places anyway. Yeah.
Right.
Great.